We begin chapter 6 with a motivating example for what's to come. So we've seen two field extensions. We've seen Q sitting inside of Q adjoin root 2. We've also seen Q sitting inside Q adjoin the fourth root of 2, where we can take a real fourth root of 2, or any fourth root of 2 for that matter, at least for this example. But there's also another one. The fourth root of 2 squared is root 2. So root 2, of course, is here, and this was the content of one of your homework problems. Show that Q adjoin root 2 is a subfield of Q adjoin the fourth root of 2. So actually there's a third extension here, Q adjoin root 2, sitting inside Q adjoin the fourth root of 2. Okay, so we can assemble the data of this in this toy example into what's called a tower of extensions. So we have Q sitting inside of Q adjoin root 2, and then that is sitting inside adding in the fourth root of 2. And each time we go up in this tower, we are actually adding in a square root. So this step here, maybe in light green, this step adds the square root of 2. Now we have access to the square root of 2, and this one adds the square root of the square root of 2. The square root of 2 is an element of the middle field, and so we're adding in another square root here. Okay, so let's just note that real quick. So that's, of course, a fourth root of 2. Okay, so we have this tower. There's actually data, and there's actually some linear algebra structure going on in the background. Namely, Q adjoin root 2, we saw how to prove set theoretically, which is a skill you should be able to do, that this is described as P plus Q root 2, where P and Q are rational numbers. That's what it is, set theoretically. Okay? And again, this is not obvious. It's something that needs to be proven, that you can describe elements of the left set as the right set. All right, so we can describe it like this, and in fact, every element is uniquely represented as P. Every element of the field Q adjoin root 2 has a unique representation like this. So any x in Q adjoin root 2 is uniquely represented as x is P plus Q root 2. So the P and Q in this situation are unique. So all I'm saying is there's one and only one way. So so as an example, there's one and only one way to write, as an example, something like 1/2 plus 2/3 root 2. If you thought you had another way of expressing it as P plus Q root 2, you would find that P had to be 1/2 and Q had to be 2/3. Right? That's the only way of doing it. And whenever you can uniquely represent something, whether it's saying it as a combination, in this case it's a combination of the rational number 1, or the number 1 and the number root 2, what this is saying is that 1 and root 2 form a basis for Q adjoin root 2 as a Q vector space. We haven't quite shown that there's a vector space structure here, but we'll see very shortly that there is. Okay, so 1 and root 2 form a basis. Okay, so what this is saying then is that the dimension, the Q dimension of Q adjoin root 2 as a Q vector space is 2, because the size of a basis is 2. Similarly, if we had any P, let's use different letters. If we have any element A plus B fourth root of 2 plus C fourth root of 2 squared is the square root of 2 plus D fourth root of 8, which is the fourth root of 2 cubed, if we have this element here, we can actually go in and we can do a trick. We can write this element as a plus c root 2 plus, and I'm going to factor out a fourth root of 2. Keep in mind, this guy here is the fourth root of 2 cubed, right? So we'll factor out a fourth root of 2. I'm going to factor it out on the right from the remaining terms. The remaining terms are these ones. Okay, so fourth root of 2. And then we'll have a b if we factor it out of the first one. And then we're only going to take out one of the powers of the 3 powers on the second one. So that's going to be d fourth root of 2 squared, which is the square root of 2 again. Okay. So let me write this slightly differently. I'm going to just add a 1 here. So just like in the previous example, where every element is uniquely represented as p plus q root 2, where p and q are rational, every element of q adjoining the fourth root of 2 has a unique representation where a plus c root 2 and b plus d root 2 are in q adjoin the square root of 2. You can uniquely represent it this way. Okay. All right. So what this is saying then, we know q adjoin root 2 is a field, and what this is saying is q adjoin fourth root of 2 as a vector space over this field has dimension 2. Because we found a basis of size 2, right? So 1 fourth root of 2 is a basis. Now, lastly, if we consider q adjoin the fourth root of 2 as a q vector space instead, which we can certainly do, what elements form a basis? Well, just like before, we still have a times 1. We're not allowed to use root 2 in our basis anymore because it's over q. So we have 1 fourth root of 2, square root of 2, fourth root of 8, which is, of course, the fourth root of 2 squared. So if we then what? Well, then 1 fourth root of 2, square root of 2, fourth root of 8 is now a basis. So in particular, the dimension as a q vector space of q adjoin the fourth root of 2 is 4. And in fact, it's no coincidence that it's 4 here and 2 before when we added a square root. We're going to formalize that. Okay, cool. Way cool. So there's vector space structure. And then the last thing that I will say here in this motivating example for what's to come is we had this extension. Let me just rewrite the extension. Well, it's a tower of extensions. We have the following tower. And it was q sits inside of q times, or q adjoin the square root of 2 sits inside of q adjoin the fourth root of 2. The big dimension here is 4. That was the computation we just did. Each one of these intermediate dimensions is 2. 2 times 2 is 4. This is a simple example of something called the tower law, which is a very important multiplicative law that we'll use that exploits the linear algebraic structure of field extensions. One last thing, keeping with this last little bit here, the basis for the first extension was 1 root 2. That was one basis we could pick. The basis, a basis I should say, for the second extension was 1 fourth root of 2. What happens if we just set theoretically multiply these? What do we get? Well, one time we just do all pairwise products is what I mean. We'll do 1 times 1, 1 times the fourth root of 2, the square root of 2 times 1, the square root of 2 times the fourth root of 2 is the fourth root of 8. Ah, that was a basis for the big extension, right? That was this basis. And that's the proof of the tower law. The proof of the tower law involves showing if you take a basis for one of the guys and a basis for another one, when you multiply them, you get a basis for the big one. So this is more or less what we're going to do in this chapter. However, there's one more additional thing called the theorem of the primitive element that I mentioned in a previous video that we'll end with, but this is the idea of the chapter.